5 images, taken minutes apart, pointed at the exact same patch of sky. 4 of them looked completely ordinary, a steady glow, exactly where scientists expected it, behaving exactly the way 5 decades of observation said it should. The 5th did not. In that one frame, a small, tightly confined patch of atmosphere had gone cold. Not slightly cold, but cold enough and dense enough that the readings didn't match anything in the other 4 images at all. Nothing about the target had changed. Nothing about the instrument had changed. Only the atmosphere itself had shifted, in the span of a few minutes, in a way nobody watching expected to see. The researcher who noticed it first didn't publish a wild theory. She went back and checked the data again, and again. It held up every time. This is the real story of what James Webb just saw at Jupiter, and the discovery that something up there is changing far faster than anyone thought possible. On March 3, 2026, a team led by Katie Knowles, a PhD researcher at Northumbria University in the United Kingdom, published the first detailed spectral measurements ever taken of 2 glowing features in Jupiter's northern aurora, known as the auroral footprints of the moons Io and Europa. The observations came from the James Webb Space Telescope's near-infrared spectrograph, and they revealed something that had never been directly measured before: how fast the temperature and density inside those footprints can shift in real time while the telescope was still watching. Auroral footprints are not the aurora itself. They are smaller, more concentrated glowing spots created when a moon's own interaction with Jupiter's enormous magnetic field sends a stream of charged particles racing down invisible magnetic field lines straight into the top of Jupiter's atmosphere, thousands of miles below. Scientists have known these footprints existed for decades. What they had never been able to measure until this observation was how quickly the physical conditions inside them could change. 538 Kelvin. That's the temperature Knowles' team recorded inside a small, isolated cold spot buried within Io's auroral footprint, the equivalent of 265 degrees Celsius. 766 Kelvin. That's the temperature measured just outside that same spot in the surrounding aurora at effectively the same moment, the equivalent of 493 degrees Celsius, close to 230 degrees hotter than the patch sitting right next to it. Minutes. That's roughly how long it took for that dramatic a temperature and density shift to appear, and in later frames fade again, a timescale so short that most instruments capable of observing Jupiter's aurora in this kind of detail have never had the chance to catch it happening at all, 484 million miles. That's roughly how far Jupiter sits from Earth at its closest approach, a distance so vast that even light, and the infrared glow Webb was measuring, needs more than 43 minutes to complete the one-way trip, meaning every frame in that 5-image sequence was already more than 40 minutes old by the time it reached the telescope's detectors. 2,000 times. That's roughly how much stronger Jupiter's magnetic field is compared to Earth's, a field so powerful that it traps enough charged particles to make the region around the planet lethal to most electronics, and strong enough to reach millions of miles beyond the planet's cloud tops, engulfing several of its largest moons entirely inside its invisible boundary. To understand why a cold spot the size of a small region of atmosphere mattered so much, it helps to understand what creates Jupiter's aurora in the first place. Jupiter's magnetic field is the strongest of any planet in the solar system, roughly 2,000 times stronger than Earth's, and it stretches for millions of miles in every direction, engulfing several of the planet's largest moons entirely. As those moons orbit through that field, particularly the volcanically active moon Io, they generate electrical currents that travel along magnetic field lines connecting each moon directly to Jupiter's upper atmosphere. Physicists call this connection a flux tube, and where that tube touches down near Jupiter's poles, it produces a glowing footprint that moves across the planet's atmosphere as the moon orbits, like a spotlight tethered by an invisible wire. Io's footprint is by far the brightest and most active of these, a consequence of the moon's own extraordinary volcanism, which constantly pumps charged particles into Jupiter's surrounding plasma environment. Scientists had studied the brightness of that footprint for years, in both ultraviolet and infrared light, and had built a general picture of it as a large-scale, relatively steady feature, one that changed gradually as Io moved through different regions of Jupiter's magnetic field over the course of hours. Io itself remains one of the strangest, most violent places in the solar system, a small moon barely larger than Earth's own, squeezed and stretched by the competing gravity of Jupiter and its neighboring moons, until its interior generates enough heat to fuel hundreds of active volcanoes, more than anywhere else humanity has ever observed. Every eruption reshapes the moon's surface and injects fresh charged particles into the space around it, particles that eventually find their way into the very flux tube connecting Io to Jupiter's poles. In a very real sense, every footprint Webb has ever photographed is a distant echo of volcanic activity happening on a small moon nearly 400 million miles away. Europa's footprint, by contrast, behaves far more gently. Lacking Io's volcanic activity, Europa still generates a measurable footprint through its own interaction with Jupiter's magnetic field, one researchers believe may be subtly shaped by the salty ocean hidden beneath its icy surface, though the March 2026 observations found its variability far less dramatic than what appeared around Io. What nobody had directly measured before was its temperature structure and density on a scale of minutes rather than hours. Jupiter's aurora is not a small phenomenon to begin with. It has been described as the most powerful and continuous aurora anywhere in the solar system, driven by an amount of energy that dwarfs anything Earth experiences even during its most intense magnetic storms. Earlier observations had already hinted that things were more complicated than the simple picture suggested. In October 2023, a separate team using Webb discovered a previously unknown high-speed jet stream in Jupiter's stratosphere, roaring along at more than 320 miles per hour, twice the sustained wind speed of a Category 5 hurricane on Earth, hidden in a layer of atmosphere no one had been able to study in this kind of detail before. In 2024, another team, again using Webb, published evidence in Nature Astronomy of unexplained ionospheric irregularities rippling through Jupiter's upper atmosphere, patterns that didn't fit cleanly into existing models of how the planet's ionosphere was supposed to behave. Each of those results chipped away at the same old assumption, that a planet as massive as Jupiter, more than 300 times the mass of Earth, should change slowly, predictably, on timescales suited to something so enormous. That assumption had deep roots. Jupiter takes almost 12 Earth years to complete a single orbit of the Sun, and its clouds, storms, and belts have been tracked by telescopes for well over a century, evolving gradually across years and decades rather than minutes. The planet's most famous feature, the Great Red Spot, is a storm system that has persisted for at least 150 years, and likely much longer, shrinking slowly generation after generation rather than transforming overnight. Against that backdrop, a 5-minute swing in temperature and density inside a single auroral footprint looked less like a minor detail and more like a challenge to how scientists had been thinking about the planet's atmosphere all along. Then came the 5 images from March 2026. Anomaly 1. A footprint expected to behave consistently across a short observing window instead showed a sharply defined region running hundreds of degrees colder than its surroundings. Anomaly 2, that same region was measurably denser than the aurora around it, exactly the opposite of what a simple cooling process would typically produce, suggesting the cold spot wasn't just losing heat, but actively accumulating more charged particles at the same time. The pairing of those two readings, colder and denser at once inside a region surrounded by hotter, thinner plasma, is what made the result so difficult to explain away. A single unusual measurement can often be chalked up to noise or a passing artifact. Two independent, physically linked properties shifting together, in the same confined patch at the same moment, pointed instead towards something real happening in the physical structure of the aurora itself, however briefly it lasted. Knowles and her colleagues concluded that the flow of high-energy electrons crashing down through Io's flux tube into Jupiter's atmosphere must be varying dramatically, on a timescale of only a few minutes, far faster than the hour-to-hour changes previous studies had documented. Something in the pipeline connecting Io to Jupiter, whether a burst of particles, a shift in the Moon's own volcanic output, or a change in the surrounding plasma, was clearly not behaving as steadily as scientists had assumed. Untangling exactly what that something was required, ruling out simpler explanations first. Instrument error was an obvious early suspect, and the team checked for it carefully, since a single strange frame out of 5 could easily have been a processing glitch or a momentary calibration issue rather than a genuine signal from Jupiter itself. It wasn't. The same instrument, observing under the same conditions moments before and after, produced entirely ordinary readings in every other frame. Whatever caused the cold, dense spot to appear had to be happening at Jupiter, not inside Webb's own detectors. The finding immediately raised a harder question. Was this rare, a one-time fluke caught by pure observational luck, or was Jupiter's aurora flickering this dramatically all the time, with nobody positioned to notice until now? In the months surrounding the announcement, some corners of online discussion reached for the biggest possible explanation. A sudden, unexplained shift in Jupiter's magnetic environment, hinting at something unprecedented happening deep inside the planet itself, or evidence of active, evolving volcanic eruptions on Io violent enough to disturb an entire planet's aurora from hundreds of thousands of miles away. It made for a striking headline. It was not, according to the scientists who made the discovery, a settled conclusion. Part of the difficulty in ruling those bigger explanations out quickly is that Io's volcanic activity genuinely can shift on short notice. Spacecraft and telescopes have documented sudden, dramatic eruptions on the Moon before, some powerful enough to visibly alter its surface within the space of a single orbit. That real, well-documented volcanic unpredictability is exactly what makes a 5-minute change in Jupiter's aurora so hard to immediately dismiss as either alien to the Moon's nature or fully expected from it. The two competing explanations, ordinary fine structure versus a genuine burst of new volcanic material, Both remain entirely plausible given what scientists already knew about Io before this observation. Knowles herself was careful to frame the result as a genuine open question rather than a confirmed answer. The team's data proved the variability was real and dramatic. It did not, on its own, prove how often this kind of rapid shift happens or definitively identify a single cause. It could reflect a burst of unusually intense volcanic activity from Io at that specific moment. It could reflect ordinary turbulence in the flow of particles along the flux tube, a kind of fine structure in Jupiter's aurora that has simply never been visible at this resolution before. Distinguishing between those explanations, the team acknowledged, would require watching the footprint far more closely and far more often than a handful of snapshots could provide. There is a reason that kind of careful, unresolved answer rarely spreads as widely as the more dramatic version of the story. A cold spot appearing and vanishing within minutes, on a moon known for violent volcanic eruptions, practically writes its own mystery. But researchers who spend their careers studying planetary magnetospheres are accustomed to results that raise more questions than they answer, and Knowles' own public comments about the discovery leaned deliberately toward caution. Extreme variability had been observed, and it clearly told scientists something new about how quickly the electron flow into Jupiter's atmosphere can shift, but turning that observation into a settled explanation would take considerably more data than 5 images spread across one observing run. That is exactly what happened next. In January 2026, Knowles was awarded more than 32 hours of observing time on NASA's Infrared Telescope facility in Hawaii, spread across 6 separate nights, specifically to track Io's and Europa's auroral footprints as they rotated with the planet. The goal was straightforward: watch long enough and often enough to find out whether the dramatic swing Webb had captured was a freak occurrence or simply the first time anyone had looked closely enough to see Jupiter's aurora behaving the way it always does. Getting that observing time at all was its own achievement. Ground-based telescope time on an instrument like the Infrared Telescope facility is heavily oversubscribed, requested by research teams around the world, competing for the same limited nights of clear, high-altitude viewing atop Mauna Kea. Securing 32 hours across 6 separate nights meant convincing a competitive review panel that a handful of strange frames from a single JWST observing run were worth dedicating a meaningful share of a shared in-demand facility to chase down. The panel agreed, which says something about how seriously the broader planetary science community took the original result. Between securing that time and completing the observations, Knowles also took the findings directly to her peers, presenting the work to international scientists at the EPSC-DPS joint meeting in Helsinki, and later joining a working group at the International Space Science Institute in Bern, Switzerland, to discuss the implications with researchers studying planetary magnetospheres well beyond Jupiter. Discoveries like this one rarely stay confined to a single research group for long. Understanding whether Jupiter's aurora genuinely flickers on a timescale of minutes has implications for anyone studying how energized particles interact with a magnetized atmosphere on any world. That analysis is still ongoing. As of the most recent update from the research team, the question of how common this kind of minute-by-minute variability really is remains open. What makes the uncertainty itself remarkable is how long Jupiter's moons have been studied without anyone catching this. Io was first photographed up close by Voyager 1 in March 1979, hovering beside Europa in an image that also captured Jupiter's Great Red Spot in the background, a snapshot that helped confirm active volcanism on another world for the first time in history. Nearly 50 years of study followed, using ultraviolet and infrared instruments on multiple spacecraft and ground-based telescopes, mapping the brightness of Io's footprint again and again. None of those observations had the combination of sensitivity and spectral detail needed to catch a temperature swing playing out over a handful of minutes. It took a telescope stationed nearly 1 million miles from Earth, built to study galaxies billions of light years away, to finally notice that a much closer, much more familiar target was changing faster than anyone had thought to check. Webb was never designed with Jupiter's aurora as its primary purpose. Its mirrors and instruments were built chiefly to capture faint infrared light from the earliest galaxies in the universe, objects so distant that their light has taken more than 13 billion years to arrive. That same extreme sensitivity, tuned to detect some of the faintest, oldest light in existence, turned out to be exactly what was needed to resolve fine, rapid structure in the aurora of a planet practically next door, cosmically speaking. Few instruments are ever built for one purpose and end up reshaping an entirely different field almost by accident, but Webb has now done exactly that at Jupiter, just as it has at dozens of other targets never listed among its original goals. You need to understand what that actually means for how scientists think about giant planets in general, not just Jupiter. If a world this massive, this far from the Sun, can show meaningful atmospheric shifts on a timescale of minutes, every existing model of how energy moves through a giant planet's upper atmosphere may need to account for far more short-term variability than previously assumed. That question doesn't stay contained to our own solar system. Astronomers studying giant exoplanets around other stars, many of them orbiting close enough to experience intense radiation and rapidly shifting space weather, now have new reason to ask whether their own atmospheres flicker this quickly too, hidden behind observations that, until now, were never designed to catch it. The story isn't finished. Knowles' follow-up data from Hawaii is still being analyzed. No one yet knows whether Jupiter's aurora is quietly flickering like this every single day, or whether Webb happened to catch one rare 5-minute window that may not repeat again for years. Either answer would reshape a small but meaningful piece of how scientists understand the largest planet in the solar system. Consider, too, how easily this could have gone unnoticed entirely. Webb's observing schedule is planned months in advance, competing against requests from researchers studying everything from nearby asteroids to the most distant galaxies ever detected. The specific sequence of images that happened to catch Io's footprint mid-flicker was never designed to hunt for rapid variability in the first place. It existed to obtain the first detailed spectra of these auroral features at all. The discovery of something changing on a timescale of minutes was, in a very real sense, a bonus finding buried inside data collected for an entirely different reason, the kind of accidental discovery that has quietly powered a surprising share of astronomy's biggest moments. Somewhere near the top of the largest planet in the solar system, a small patch of glowing atmosphere just proved that even a world 12 times wider than Earth can still surprise the people watching it, one 5-minute flicker at a time. If you want to be there when that answer finally arrives, stay close. Jupiter isn't finished changing yet.